Okay, here is our third revision topic on waves. Okay then, what causes waves? Well, what we usually have is vibrations that cause waves. And if those vibrations are in right angles to the direction of motion, then we end up with a wave looking like this. And we call that type of wave a transverse wave. Okay, a very good example of this one is light, or anything from the electromagnetic spectrum. There's one other way that wave can occur, and that's if the vibration of the particles are actually in the same direction, or in the same plane as the direction. And therefore, we end up with, and we often draw this slightly differently, we end up with, this is a wave looked on from above, we end up with a wave that has compressions, and these areas which are spread out called rarefactions, and that is a longitudinal wave. And we often, if we need to use an example, we often use sound as the example for a longitudinal wave. Longitudinal wave has these compressions, whereas a transverse wave have these peaks, like the equivalent positions. And we have these troughs, whereas we have these rarefactions. Okay, excellent. Now, obviously we'll need to quite often quantify what we're seeing with these waves, and so what we have is we often draw them in this graphical form. Now this is where we need to be very careful. With this graphical form, this axis will always have, well, both axes should always have a label. This is the one you're looking at particularly carefully. If it's a time axis, then when these waves are drawn, then this particular length or difference is known as the time period of a wave. Time period of a wave. The time it takes for one wavelength to occur with the wave. If, for example, this were 1 second, 2 seconds, and 3 seconds, then my time period, given the letter t, here would be not 1, that's half a wave, 2, because that is one wavelength. Okay, so time period of a wave, an important idea. We also might want to talk about the frequency of a wave. And the frequency of the wave, which is measured in hertz, is equal to the number of waves per second. So the number of these waves that occurred in a second. So if we look at this diagram, of course, in 1 second we only have half a wavelength occurring. So therefore the frequency will be half, but we always write it as decimals, 0.5 hertz. Okay, now you from the definition you can work that out. However, there is a quicker way to work it out, and that's to say that the frequency is 1 over the time period. You can mathematically do it yourself. In this instance here is the example. My time period was 2 seconds, so 1 divided by 2 gives me 0.5. Hertz, of course. Check, check, it works out. And there is a triangle for it as well, which is this. It's a bit strange because this is a number 1, but it still works adequately. Okay, so let's look for an example. Here is an example for you. It's going to be graphically shown this example is, and we are going to have our wave. We are going to have 0.25, this is time again. Okay, 0.25, 0.5, 0.75. So now what I want you to do is work out the time period and work out the frequency. Think you know what you're doing? Hit pause, or I'm going to go straight to the answer right now. Okay, so the time period, Well, that's quite straightforward because it's the time takes for one wavelength to occur. You need to be sure you can identify that as a wavelength, one cycle of a wave there. So we've got 0.5 per second. Okay, what about the frequency? Well, two ways of doing it. First of all, you say, well, how many wavelengths have occurred in 1 second? Well, if that's quarter of a second, that's half, that's 3/4. In 1 second, we would have got 1, 2 wavelengths coming at 2 Hertz. Or, mathematically, we can say, well, it's 1 divided by the time period, 0.5, which gives us 2 Hertz. Okay, so it checks out. Good. Okay, here's one last example. What happens if I was looking at water waves? And I saw 20 waves in 5 seconds pass a point. What is the time period and what is the frequency? Hit pause, give it a go. Otherwise, here's the answer. Well, the time period is essentially, if I know that I've got 20 waves in 5 seconds, then how long has it taken for one wave to occur? Well, 5 is the total number divided by 20 gives me, goodness, I've just had a brain, 0.25 seconds for one wavelength. Hold on, what I'm saying is the frequency there. Hold on, sorry, slight error. So the time period here, how long would it take for one wavelength to occur? No, that's right, sorry, yes, that is right. So 0.25 seconds, the time for one wave to pass. So therefore, what's my frequency? Well, my frequency is 1 over 0.25. Or, if you prefer, you can say to yourselves, well, if I've got 20 waves in 5 seconds, how many must have occurred in 1 second? Well, it must be a fifth of that, giving me 4. And if you do 1 divided by 0.25, you get 4 Hertz. So it does work out. Brilliant. Okay, let's put that to one side for me a moment. Let's now talk about how this graph might look. Remember I said you need to be very careful and look at this axis here, because before it was in time, what happens if this was a length? Well, if it were a length, then what would be shown here would be the same looking type of wave. However, this point here would now represent the wavelength, not the time period, but the wavelength of that wave, given the symbol lambda and measured in meters. Also, something else you can infer from this is this distance here, and that's known as the amplitude. The amplitude, in effect, saying the maximum distance from the position of rest to the maximum displacement point is the amplitude. So you need to bear that in mind as well. So we've talked about the frequency, the wavelength, the amplitude, the time period, and finally, we get to talk about, well, actually, sorry, wait, let's just pause there. Let's look at sound waves, because they do use slightly different terminologies. That being, first of all, sound needs a medium to travel in. In other words, it needs a material. You won't get sound travelling in space because space is a vacuum and there is no material in space. Okay, so how fast does it go? Well, the speed of sound in air is 330 meters per second, which is pretty fast. However, that is much slower than the speed of sound in liquids, and that indeed again is much slower than the speed of sound in solids. The reason being that as you get more tightly packed atoms in liquids and solids, so the vibration can move faster through them. Okay, and finally, we often talk about the frequency of a sound, but that is referred to as the pitch of a sound. And if we're talking about the amplitude of sound, that's often referred to as the volume. of the sound. Excellent, right. Let's turn now to our concept of speed. I'm just going to write this equation down because it's one you're going to have to use and manipulate quite a lot. Wave speed is equal to the frequency times the wavelength. Or, if you prefer symbols, V is F times lambda, remember that odd symbol, but lambda. Meters per second, the speed is measured in, hertz is the frequency, meters is the wavelength, and if you want the triangle, then that triangle will serve you very well for these solutions. Excellent. Okay, so let's use an example to work out how fast a wave might be travelling. Let's use that example before. We said 20 waves pass a point in 5 seconds. So therefore, what's the time period of that wave? You can hit pause and try it again, but quickly we said that, well actually, 20 waves passing in 5 seconds, that must suggest that you have, in one wave, you must have 0.25 of a second. The frequency, therefore, is 4 Hertz. It's 1 divided by 0.5. If you want to, you can skip back and have a look why, if you've forgotten. Now, you know that much. And what would happen if I said, well, actually, I measured the difference. Let's measure these water waves. And I measured the distance between them of the two peaks at 16 meters. What's the wave speed? Okay, if you think you know, hit pause and give it a go. Otherwise, here comes the answer. Well, the wave speed is simply frequency times wavelength. We have our frequency of 4 Hertz, and I'm going to multiply that by 16, giving me 64 meters per second. I'm just wondering if that's right. That seems rather fast for a wave. But hey, nonetheless, doesn't matter. The logic holds and the logic works out. So, right, next example. Let's try a slight rearrangement of those ideas. Let's imagine now that we have a sound wave. Let's imagine we have, remembering here, of course, that the velocity of sound is 330 meters per second. Let's say we have, I don't know, C sharp, which is approximately 330 meters per second. I'm not even sure if that's a sharp symbol, I'm not a musician. And that's 330 Hertz, should I say. But I definitely know that C is approximately 330 Hertz. So knowing that information, what is the frequency of that, should I say? Knowing that information, what's the wavelength of this sound? Think you know the answer? Hit pause and give it a go. Otherwise, here comes the solution. Right, we know what equation we're using. Of course, we need to rearrange it and plug in our data. We know it's 330 speed, we know 330 Hertz, and so that gives us 1 meter. 1 meter between the crests of this longitudinal wave, or the compression, should I say, because it's longitudinal. Okay, and now the very last bit we dealt with was the electromagnetic spectrum, a really important part of physics. And in essence, what it is, it's a vibration, and this vibration occurs in the electric and the magnetic fields. You're familiar with these regions because you know them as radio, micro, infrared, visible, ultraviolet, X-ray, and gamma rays. And essentially what they are is they're slightly different frequencies of this same vibration in the magnetic and electric fields. But we've grouped them together in these seven regions. You'll notice, of course, that the wavelength is very large there and the wavelength is very small there. However, the frequency is very, very large here. and very small here. And you have these movements between the two, of course. There's also, of course, another bit, which is the visible light is red, orange, yellow, green, blue, indigo, and violet. That's what it's made up of. Notice here the red is near the infrared and the violet's near the ultraviolet. And the electromagnetic spectrum travels at the speed of light, which is 3 × 10⁸ meters per second, super quick. And it can travel through space because you don't need a medium to travel through, because there is still an electric and a magnetic field in space which it vibrates in. Okay, let's just look at some uses and dangers very quickly. Radio, communication, anything from TV to radio, ship-to-shore radio. Microwave is mobiles, and cookers as well. Microwave cookers use microwaves to heat the water. Infrared are sort of toasters and anything that are warm in the fire. The fire will heat the air, but the way it heats you when you feel a fire being hot is the infrared that's been given off the coals. Visible, we have micro and telescopes. You're manipulating light. Ultraviolet, obviously tanning. People enjoy tanning, and security as well. If you look at, say, a bank card or a £5, £10 note under a UV light, you'll suddenly see it reflecting things that it didn't before. So security can use this to guarantee they are kosher, they are the proper notes, not forgeries. X-rays, of course, I'm sure you've also had pictures done of yourselves or seen pictures of X-rays. And also they kill cells, which can be used in some types of medical therapy. And gamma rays are so powerful they sterilize because they kill all types of cells, including bacteria, which are dangerous to you, and they're used in some types of therapy. However, of course, you can notice that there is this increasing danger. For this end is very dangerous, decreasing to little danger at this end, but it's always increasing. And so therefore, people aim to stay away from these, and they don't worry too much about those. Okay, that's the waves topic complete.